So this part looking at ways to calculate work. So I'll look at two new equations here, slightly new. Um, so we've talked about total initial energy being the same as the total final energy. Total initial equals total final. With our open systems now, it's total initial energy plus work equals total final energy. And the work has to be done by something outside of our system. So if we have this equation, one way that we can calculate work is to say, hey, if I know my total initial energy and I know my total final energy, the work is the thing that accounts for whatever's missing. And if I wanted to get W or that work done on its own and just solve for W, well, I could subtract total initial energy from both sides and we'd rearrange and get to the work done on our system is total final energy minus total initial energy. And that works delightfully well. So total final minus total initial equals work. That works. Or we could kind of just leave things as they are using the example problem that we had. We could say, hey, work, we had in that example problem, 0 plus work is the kinetic final plus the gravitational final. And we could just solve for work that way. That works perfectly well. That's one way to solve for work using these energy equations. Another way is that work equals the product of multiplying the average force times the change in position, assuming that they're going in the same direction. They're both going either the same line. Uh, so they're either both going to the right, both going to the left, they're both going up, they're both going down, or up, down, one's up, one's down, the force and the displacement, one's left, one's right, the force and the displacement. If we have one at going to the side and one kind of up at an angle, well, it's still possible to figure that out, but we have to do a little bit of geometry or trigonometry bits where we say what part of this thing is going that way. It gets a little bit messy. We won't do that in Physics 9, but it's definitely possible. It's within your capabilities. It's just we don't have the time to go through and figure all that out. But the two ways to find work, one, this energy conservation bit we set up here. The other is to go through and say, hey, we're going to take average force times the change in position. If they're both in the same direction, then we get positive work. If they're in opposite directions, like an average force to the right while the object moves to the left, well, then that's negative work being done. Like one of the Spider-Man movies, right? The kid Spidey is on a train and he kind of goes out front and he has to stop the train. So he like and throws the little Spidey web or whatever out, and he's kind of getting all stretched out trying to stop the train. Well, the train is going that way while he's pushing that way to try to stop the train. So Kid Spidey is doing negative work on the train, trying to slow it down and stop it. So negative work is done when objects outside the system change the energy of the system. That's work. It's negative work if the distance it moves and the direction of the force are in opposite directions. That means then that the total energy is decreasing. Work is negative if the total energy decreases, or if the object pushes one direction while the system moves the other direction. So we can go back to this, right? I'm pushing up on my mug, but if I do this in a controlled manner where I push up but go down, well, I'm removing gravitational energy from my mug earth system. My push by my hand is removing gravitational energy of the mug earth system. So it's possible to have negative work if the force and the change in position or the force and the displacement are in opposite directions. So we'll look at an example problem. So our example problem, let's hope it still sticks with us here. I don't trust that it is. There it is. Okay. So now our example problem, it's the exact same setup as before. We still have the cart, the track, the spring, the earth, all those things. Now our adjustment to how we're studying it is just to say that the earth is outside of our system. So everything exists in the same way. Everything behaves the same way. Our analysis is different. So if we're looking at this in the beginning, we can open that up and take a look. Um, and we see that as we're going through, remembering the spring is in our system. When the cart is at A, all the energy is stored in the spring. The spring is in our system. So all of the energy stored within that spring is um, in our spring, in our system. So we can include that now as energy in our system. And I'm just going to say, hey, we've got all that energy in our system. We're just going to make that 4 bars of energy. We have 4 bars of elastic energy in our system because our spring is a part of our system. Energy is in that spring. Um, and then we can go to the final part. We're saying here the Earth is not in our system. So if the Earth is not in our system, then we have this weird deal where if the Earth is not in our system, we cannot have gravitational energy. We can only have gravitational energy if there's an object with mass, there's a gravitational field, there's a height above zero. All of those are true right now. But that last condition, the Earth has to be in our system because it's that gravitational energy exists due to an interaction between the Earth and the object. That interaction continues to exist, but both of those objects have to be in our system for that energy to be within the system. So, since the Earth is not in our system, there is no gravitational energy. And before we had 2 bars of kinetic energy, so I'm just sticking with that. Changing how we analyze the system will not miraculously give us more energy. So we start off with 4 bars of energy, all in our elastic band, or all that energy in our system is elastic energy in the beginning. We end with 2 bars of kinetic. So right now we've got an issue. We know 4 does not equal 2. So we need to look at this workflow diagram and figure out what's being done. So we'll open that bugger up. And now, as we're looking at this, knowing that the Earth is outside of our system, and we've gone from here, we'll close that again. Sorry. We've gone from 4 bars of energy in the beginning to 2 bars of energy at the end. We've lost 2 bars of energy. 2 bars of energy have left our system. So to show that those 2 bars have left our system, we're going to take this arrow and have it point out instead of pointing in. We have energy leaving our system because of work that the Earth did to our system. So when so um, the car was coasting up on its own. Like if we throw something, I'll throw, uh, hmm, right? So while that's going up and down, well, while it's going up, it goes up, and gravity is pulling it down, removing energy from this thing. If gravity didn't exist, this thing would just keep going up at the same speed. So the Earth and its gravitational energy, or pardon me, the Earth and its gravitational field and force interact with that object to remove energy from that object and the rest of our system. Come on. So we now have lost 2 bars of energy. Those 2 bars of energy have left our system. And if the energy has left our system, that makes it negative work. Or the object is moving up. That little cart is going up the track while gravity is pulling down. So we know it's negative work, and it's negative work done by the Earth on our system. So we say it like that. That's a little awkward. There we go. So negative work done by the Earth on our system. And then when we go down here to look at an equation, we could say something like, hey, we have the elastic energy initial, and then we have work that's being done. It's negative work being done by the Earth. And that equals, oops, the ending energy that we have, EK final, uh, at position B. So we've gone through and we've done the same sort of thing for every one of these problems. It's just that in different cases, we would have different types of energies or different ways to analyze our system. So if the Earth is outside of our system, we don't have any gravitational energy. If the Earth is in our system, we have gravitational energy. So right now we have elastic energy in the beginning. The Earth does negative work on our system, and we end with kinetic energy at the end. There you go.